Hello everybody, we'll have a different lecture today of applications of optimal control theory. And so far we have seen linear quadratic regulator design, lot of details about that. Okay. And then we have also seen this flight dynamics in fair detail actually. So, we will go back and try to kind of relate these two concepts, and then can ask the question whether we can do this missile guidance using LQR. Okay. So, that's the topic of this lecture, and let us have a quick glimpse of what all we can do through LQR theory. And very nicely it will fall down to the same classical control cases and all that we will derive it and so. And one of that you have already seen in one of the previous lectures actually, but here we will have a different case derivations and things like that, and ultimately you will be able to see little more generalization of that concept in addition to what classical theory gives us actually, classical missile guidance theory gives us. Alright, so the topics of this lecture is something like this: a little bit basic fundamentals of what are missiles, what are classifications, what are components, things like that. Then one quick glimpse of what is this philosophy of this so called proportional navigation guidance. Okay. Then we will try to revisit this LQR theory, and then formulate the problem in the framework of linear quadratic optimal control, and come up with optimal missile guidance actually. Then in that framework we will study various classes actually, mostly in 2D. This is proportional navigation guidance, augmented proportional navigation guidance, then the same derivation through this zero effort missed concept, okay, of the PN guidance, and also aspect angle constant guidance actually. We will have some concluding remarks at the end of the lecture. So, very quickly some basic fundamentals of missiles and then components, things like that. So, classification of missiles, you can have various classifications, and the very basic thing that comes to mind is either you have surface to surface, surface to air, or surface to air, or air to air, or air to surface. And when somebody talks about surface to surface, that can either be strategic, okay, or can be simply tactical. Okay. So, strategic missiles have typically large impact. They normally carry some sort of a nuclear warhead and things like that, but then they are normally not used. Very rarely used. So far we know that only one time it was used in Second World War, that's all actually. But tactical missiles, which are limited impact but targeted impact, and that is where the usage becomes much more, because you don't want to have collateral damage, and you don't want to have unnecessarily large damage and things like that actually. So, that is where tactical missiles come in. Then surface to air is largely defensive nature. Okay, so if you know for sure that some enemy is attacking and all that, before it does some harm, we have to kind of nullify that. So, that is the surface to air sort of missiles. Then air to air is it is also kind of a defensive missile, or it is something like air combat usage. Then air to surface is largely attacking sort of thing actually. Okay. So, all sort of things, different classifications somebody can do in various things. In a different sense, they can also be classified in different ways. Somebody can talk about tactical versus strategic. I already talked a little bit about that. And then somebody can also talk about exo-atmospheric versus endo-atmospheric. Okay. That means finally the interception happens beyond atmosphere. That means aerodynamic forces and movements are not valid there. Okay. Or it can have endo-atmospheric engagement, where we are still talking about engagement within atmosphere actually. Okay. So, obviously aerodynamic force and moment play a large role there. Then you can classify from ballistic versus cruise. Okay. So, ballistic missiles largely follow so called ballistic trajectory. In other words, the motion is largely influenced by only gravity, okay, or possibly by drag only, but there cannot be any lift and things like that. Okay. Alright, then on the other hand, there is a cruise missile. It is almost like aircraft, very close to earth it travels, and then travels for a short range, long range, depending on the mission and things like that, but largely it travels because of the lift like aircraft. There are various pros and cons obviously. Ballistic missiles you can cover large distances with less energy, whereas cruise missiles is susceptible. It has a good amount of stealthiness actually. Okay, that means because of the earth curvature, unless and until the vehicle is very close to the target that the enemy cannot detect it actually. Okay, so that advantage of cruise missiles anyway. And then somebody can also talk about from long range versus short range, depending on how far you want to go and things like that. And then there are criterions like solid propulsion versus liquid propulsion and things like that. And that's a major departure, by the way. There are various issues with respect to solid propulsion and liquid propulsion. I think one of that we will talk a little bit when we go ahead in the lecture series, a little later actually. So, and this is not end of the story. And somebody can, various classifications also exist other than these things. And it doesn't matter so much actually. The fundamental physics remains same and fundamental ideas remain same in a way. But depending on the nature of the problem and depending on missions requirement, all things can be different actually. So, typically components of a missile you can classify something like this. So, there is something like a command signal receiver at the end, which can receive commands from ground station radars and things like that. And then you have various components coming on, various components of a vehicle is very tightly packed, by the way. The inside things, the space is very limited and then is very tightly packed typically. Here you can see there is a radome thing. Okay, so this actually protects the vehicle from aerodynamic loading and all that. And this part is a very sensitive part. This is where your all seeker and then the sensitive instruments sit actually. Okay. And next to that is warhead, okay, and then flight control system can take care of, somewhere situated somewhere here, and then you have these fins there, and then these wings here, and then fins here, things like that, aerodynamically actuated surfaces. Then you have this propulsion system somewhere here, okay, and then this configuration is not unique, by the way. It can have various configuration depending on the design part of it actually, but largely these components are part of the vehicle. It has to have propulsion, it has to have guidance system, it has to have seeker system, it has to have various other things, warhead of course, it has to have various other systems that are necessary for a missile actually. Yeah. Alright, modes of operation. Typically when we talk about, we are not bothered too much about propulsion structures, things like that. We are all bothered about navigation, guidance and control. So, that is the primary motivation for us to see something actually. So, the navigation is nothing but determination of the current position. So, it all that it does is using some sensors and that is a big task of course. Using some sensors, it finally finds out where the current location is, typically in the inertial coordinate frame actually. So, that we have this so-called INS sensors, inertial navigation system, we have this GPS systems and we have this diffuser of these, magnetometer, many things are there, which actually tells us the current position of the vehicle, and in addition to that the current velocity vector coordinates of the vehicle as well. It does not talk only about the position, okay. Position and velocity it will give us actually, and both in kind of translational motion as well as in rotational motion. That means attitude and attitude rate also it will tell actually. Then after you know all that from navigation system, the next task is guidance, and that is nothing but determination of a strategy to dictate a flight path actually. Okay. So, in other words, we have an objective to meet going from point A to point B. So, this guidance system will come up with a strategy to dictate a flight path actually. Okay. So, the aim obviously of the ambition of that flight path is to lead the vehicle for a successful interception actually. Okay. So, the navigation followed by guidance, and that is what largely we will talk in this lecture. And after that is done, the next task is control, where also largely it is known as autopilot in the in the missile community. And it is that the objective here is determination of the required control forces and movements, so as to enforce the missile to follow the guidance command. Okay, this gives the status of the vehicle, the navigation system. Then guidance gives the way to go, the flight path to take and all that. And the control or the autopilot essentially generates all the necessary control forces and movements to ensure that the guidance path is followed actually. It means whatever the guidance is giving as a command, it is actually getting tracked by the autopilot system. So, all the three are in unison really. If the one system fails somewhere, the entire mission will go bad actually. So, everything should have lot of correlation and everything is important actually. for a successful mission. But in this particular lecture, we will largely concentrate on guidance aspects actually. So, what is guided missile? Formal definition sense, somebody can write it this way. A guided missile is a unmanned flight vehicle which is usually fired in the direction of approximately towards the target. Of course, you will not fire in the reverse direction. It has to be fired approximately towards the target and subsequently receive the steering commands to improve its accuracy. And the steering command can either come from onboard sensors or with external aid also basically. Okay. So, that's what the guidance of missile concept is basically. And again, you can various guidance laws have been proposed in the literature over several years, and this if you compile everything, so this tactical missile guidance laws and all that. And then you can have various classical or empirical laws, you can have various mathematically rigorous formulation, and that is what we are going to do it in this lecture particularly. Then you have this optimal control class of guidance laws, and you can also have something like predictive guidance, which we will slightly do later in this course. And then the differential games ideas also, which unfortunately there is no scope to talk about it here, but there are also nice ideas where the capability of the target is equivalent of the missile's capability, something like that. So, the target behavior is equally capable basically. In those situations, this differential game guidance becomes much more useful actually. Okay. A kind of extension of optimal control theory, you can say that. We will not talk too much on that. Largely, we will concentrate on optimal control based things, and then subsequent lectures we will talk a little bit ideas on predictive guidance, which is very effective actually. Okay. Anyway, coming back to that, the classical and empirical thing can also be classified in some sort of two ways. One is this conceptual sort of ideas, and then implementable sort of ideas actually. Okay, so something can be conceptual means, okay, it starts with very neat ideas and all that, and then it's mathematically it is very rigorous, it's very appealing rather, but there will be some sort of practical implementation difficulties and all that actually. So, those things will be slightly modified, and then in this side of the branch results actually. Okay. So, you have this PN class of guidance. If you see, PN falls in here. Proportional navigation is true proportional navigation and pure proportional navigation. And if you also come from optimal control theory, you will also land up with this TPN, PPN and augmented PN also basically. So, we will see that in this particular class, how these things which has already been proposed from geometrical consideration can also be mathematically rigorously shown that they are nothing but optimal optimal guidance laws actually. Alright, so this is a summary of all these guidance laws. And in general, overview sense, what is a broader picture of a flight control system? The objective is to deliver a flight vehicle from its current state to a desirable final state using the available information and available actuation, okay, while satisfying all physical constraints on the vehicle. So, you cannot talk about ignoring these things. Physical constraints such as like angle of attack constraint, lateral acceleration constraint, or even various body rate constraints, actuator constraints, all sort of thing will happen actually. So, those constraints has to be honored, and within those constraints, it has to deliver the flight vehicle from its current state to a desirable final state. Obviously, it has to be the target interception point and all that actually. Alright, so that is the objective. Then, what are the desired terminal states then? There can be several applications in different ways. One can be simply rendezvous problems, where things can simply come and join together and continue to go together. That means, position sense they will be very close to each other, but velocity sense there is no relative velocity between them actually. So, that means they continue to coexist sort of thing. The very good applications, for example, aerial refueling and then formation flying control and things like that actually. Then there is interception, where we are largely interested in this lecture, okay, to nullify the target with appropriate interception. That means, velocity vector need not, relative velocity should be as high as possible, while the position vector should be 0 actually, this interception. Then also like some desired terminal states can be simply orbital parameters when somebody talks about just launching a satellite. So, what is the final desired condition? There is nothing but any orbital parameters on the orbit from where it will continue to circulate actually. So, that's why depending on the various flight applications, aerospace applications, you can talk about various flight control system actually. Now, it talks about available information. Okay, what are the available information? First of all, own state vector. It is largely through the own rich sensor information. With this information is typically very good, because the sensors are very smart these days. Within they have their capability is much higher, and then the noise component is almost negligible actually. So, the own state vector is very much reliable, and that is what is available from the INS system or entirely this navigation system from the vehicle actually. Then the other available information is terminal position, okay, for the stationary targets, or the instantaneous relative position and velocity for the moving target, either using a radar or seeker or things like that. Okay, so in this case, there is a need to estimate where the target is likely to be at the final time, and that is where you want to go, not to the current position of the target, but where it will go at the final time. That is where you want to go actually. So, that's what the missile guidance concept is. Then there are actuators. So, we have various types of actuator. We have aerodynamically controlled actuator. So, such as fins, canards, spoilers and things like that, which are typically useful within endo-atmospheric engagement actually, okay, where you can generate lifts and moments and then manipulate that. And these are very good, because normally these aerodynamic forces and moments are what we call as they are available free actually. Well, not really very free, because you have to deflate the fins and things like that, but almost free in the sense the lift vector is anyway there, you just have to tinker a little bit and then you get a huge impact on your vehicle actually. So, that is that very little effort, but the output is very good actually. So, wherever aerodynamic controls are available, the recommendation is to go for that actually. Then there are thrust vector control, such as like engine swiveling, side injection mechanism, and then nozzle deflection mechanism, things like that, by which the thrust vector is purposefully deflected away from the missile's axis, own axis basically. Then you will get a lateral component of that, which will give you some sort of moment to turn actually. Then there are reaction jets. Okay, you can also talk about cold RCS or hot RCS like that. And again, depends on that. Cold RCS means you have just pressurized gas and just you let it go to expand through a nozzle. Whereas hot RCS means you actually a small rocket engine sort of thing, where you actually burn and get your thrust and then deflect it through different jets and all that. Anyway, so then there are divert thrusters, such as vernier thrusters. These are typically located at the CG for very final corrections at the end actually. Okay, because they are not the correction doesn't happen through moments here. It directly happens through the through the translation motion of the vehicle. Vernier thrusters are typically placed close to CG. So, directly it will translate wherever you want. Obviously, the capability will be lesser. So, people do not do it just like that, but the very end, suppose you want to correct certain small error, then it's worth doing it actually. Alright, so then conventional flight control system is typically designed this way. We have this outer loop guidance, obviously one loop, with inner loop autopilot. That means, whatever guidance command gives, lateral acceleration commands and things like that, that inner loop has to track, and this inner loop is again divided, it can be synthesized either in 2 loops or more than 2 loops actually. Okay. So, that means 2 loop means typically the guidance command gives us gives us lateral acceleration commands. The guidance loop will give lateral acceleration commands, and then inner loop autopilot will convert that first to body rates, namely pitch and yaw rates, and then that is one loop, and then it will convert, then it will try to track those pitch and yaw rates using control surface reflection. That is one more loop. So, minimum 2 loops are necessary in that. And more on that, people sometimes put integral feedback for better performance, and then you have these actuator loops inherently sitting there, things like that. So, you have at least one loop in the guidance, and then inner loops are there, at least 2 loops in the autopilot. This concept was developed around 1950s, where many missile guidance ideas also got developed. And then it also accounts for limited onboard computational capability, because each of the loop means a small subsystem sort of thing. So, you do not have to computationally burden your system. Then limited analysis and design tools are typically adequate because the dimension of the system is not large, complexity is not large, things like that. And then the lower expectation on the vehicle performance was also a factor for such a synthesis loop actually. And towards the end of this course, we will also see whether these concepts can be relaxed, and people now talk about integrated design approaches, integrated guidance control, things like that, where these loops can be minimized as much as possible actually. Okay, then the next point is adequate for it turns out to be typically adequate for stationary and non-maneuvering targets, or rather little bit maneuvering, that means less maneuvering targets also it will do the job, because the guidance law and control design gets several updates on the way basically, that's why it happens. And ultimately it actually results in simpler guidance laws. Typically this PN guidance, pursuit guidance like that, it will result in that. Those are very simple to implement also basically. So, what are the objectives and mechanics of machine guidance? Objective is to control the position and velocity vector to cause interception subject to constraints. That is a straightforward objective. And mechanics of guidance is to manipulate the position through changes in the velocity vector. That is how we can influence that. So, you have to manipulate the position through changes in the velocity vector. But how do you do the changes in velocity vector? That is through the control. So, the control the velocity vector magnitude either by manipulating the thrust if possible, or by minimizing the drag also. That is the way of doing that, but that is only for range enhancement and things like that actually. I can also change the control vector magnitude by applying forces normal to the velocity vector. That is control the velocity vector direction rather, sorry. Okay, this is not magnitude, but this is direction. Okay, you can always control the velocity vector direction, and that is what is done typically largely by applying forces normal to the velocity vector, and that is where the course corrections happens actually. Alright, so what are the difficulties of missile guidance? First of all, target related information is not readily available. So, target related information, target is not going to give us free actually. So, obviously, we have to estimate the target information and that is a must actually. In fact, it turns out that the final missed distance is a strong function of target estimation behavior or properties actually. So, that is a very important factor. We should not miss out actually, even though we are not talking in this class basically. Anyway, so then what are the mechanisms for applying forces normal to the velocity vector? You can have a direct lateral thrust or something like divert thrusters, or you can have something like lateral components of the main thrust vectors. There is thrust deflection and all that. So, if you deflect the thrust, there will be a lateral component which will generate moment and all that. And also there is a aerodynamic forces that can be generated by this angle of attack and side slip angles. If you can generate both together, especially you can do that when you have two planes of symmetry like 4 fins and all that. In a missile setting it is possible. So, that means you can consider the side slip angle as something like angle of attack, and then it will be like both angle of attack and side slip angle can be generated utilizing the control surface reflections, and that concept is called skid to turn. And suppose that mechanism is not there, the vehicle has only 2 big wings and all that, that is also possible, and especially for long duration practical things, typically people do that to minimize the drag actually. So, when you have something like that, you have also longer time for doing your corrections, and because of that there is a concept called bank to turn, where you have the control influence is given to the vehicle through angle of attack and bank angle commands actually. So, either you directly generate force fin deflections and generate 2 moments in pitch and yaw and directly go there, called skid to turn, or you have the bank in the appropriate direction and then apply the control. So, that you can go towards that, and that is called bank to turn actually. And largely it is typically done skid to turn in missile things, and other applications such as aircraft or UAV control, things like that, these are typically bank to turn actually. Okay. There are several undesirable consequences also. Everything does not happen so nicely that we like to see, and then first of all, lateral force components are not happening at the CG. Obviously there are undesirable moments actually, and largely that they also result in non-minimum phase behavior, especially when you have tail control vehicle. Okay. And then the vehicles are also designed aerodynamically unstable. They are not designed stable, by the way, because they are designed unstable because to have better LYD ratio, lift versus drag ratio, lift over drag ratio, and better maneuverability also, because lift will be high and all that actually. Hence, the motion arising from the maneuver forces may destabilize the vehicle also. That means, if you don't do a very careful exercise, the vehicle is inherently unstable. So, if you excite a little more, and then it will go to rotational instability very quickly actually. Okay. And also remember that large lateral acceleration command is a sad reality. That means, the targets are becoming more and more powerful, they have more and more maneuvering capability and things like that. So, we do not have the luxury anymore not to have large lateral command acceleration. I mean, these modern day missiles are typically they have to have large lateral acceleration, especially these defensive tactical missiles actually. So, for example, some air to air missiles also talk about 20-30 G of lateral acceleration actually, that is quite large actually. So, that is a sad reality. And whereas the rapid command response is a bad necessity also. Okay. So, that is where you have to be extremely careful that okay, some effects do not come which will destabilize the vehicle actually. So, these are typically difficulties of the missile guidance thing. Then applications of guidance theories, I mean, before we go ahead, I thought it is good to see this, because even though without loss of generality we are talking about missile guidance here, but the same concepts can be used in several variety of applications, including torpedo guidance, robotics, smart cars, even collision avoidance. Okay, that means missile guidance is all about collision, but you can also have problems exactly opposite, where you can talk about collision avoidance, safety, basically safety considerations. Can also use the similar concepts for formation flying, automatic landing, spacecraft docking, air to air refueling, and whatnot actually. There are several domain or applications areas where this guidance theory is very much useful actually. Alright, so let us go ahead with a little bit fundamental problem of tactical missile guidance and see some of the concepts very quickly. So, the engagement is typically like this: you have a target which is running away from in this direction with the velocity Vt, and there is a chasing vehicle which we call as missile, which is having its velocity vector Vm, and ultimately it has to go and hit the target. And normally it does not happen automatically. The whole idea here in the very beginning sense is something like this: if you continue to go in this direction, it may not go, because this may run away. So, you have to take a little bit course correction and the direction change essentially, so that ultimately both the vehicle as well as the target will go towards the same intercept point actually, and finally they will intercept each other. So, this course correction is typically done by applying a lateral acceleration command, which can either be perpendicular to the LOS vector or perpendicular to the missile's own velocity vector. Okay. Obviously, if it is proportional to the LOS vector, okay, things are mathematically good, because ultimately this guidance relies on the philosophy that the LOS vector should not rotate. See, if initially it can rotate, but after some time this LOS vector, instantaneous position 1 for the missile and position 1 for the target, position 2 here, if you can keep on joining that, then this LOS vector should remain parallel to each other, they should not rotate actually. So, that is the concept that was used in SIP guidance and all that before, and that is where the concept, the terminology is borrowed, like proportional navigation, even though this is a guidance concept, nothing to do with navigation really basically. Anyway, so these are the two variations. If your aim is to make sure that LOS vector does not rotate, then obviously the lateral acceleration command that needs to be applied should be perpendicular to LOS actually. That is where it is mathematically more elegant. Okay, conceptually that's the thing. But again, practical difficulty of implementation do exist, because if you have something perpendicular to LOS vector, then obviously it will have a component along Vm, and component along Vm means component along thrust axis direction typically, and that is normally not possible to manipulate. Okay, may have a drag, but drag is not a control variable, you cannot manipulate that actually. So, the idea here is, why don't we apply a force which is perpendicular to the velocity vector then, okay, which is easy to implement, because I do not have to worry about the other aspect, that I cannot really implement the other component actually. because by design I am reflecting something which is perpendicular to velocity vector, which I can generate through my lift generation mechanism actually. So these are the two concepts, and depending on that we can have two variations of that. And if it is something like perpendicular to the velocity vector, it is called pure proportional navigation, which is the concept is like this. You have this sigma dot, which is sigma is the LOS angle with respect to arbitrary reference lines, but what is more important is sigma dot. So, the guidance law talks about AM equal to navigation constant n, which is a number, times Vm, velocity of the missile, times sigma dot. And on the other hand, true proportional navigation tells that okay, I will not apply it perpendicular to the velocity, I will apply it perpendicular to the LOS rather, and my lateral acceleration command happens to be NVC times sigma dot, and it is not Vm, remember that Vc is the closing velocity along LOS actually, okay, times sigma dot again. So, this is the fundamental concept of 2D missile guidance in general. So, now if you talk about engagement models in 2D and all that, you can have the same, so you can put a inertial axis frame, and then probably it's and in the y direction you can see that I can write, I mean the reference line happens to be parallel to the x axis, other one is perpendicular to that, and then you have this sigma, which is approximately sin sigma, provided sigma is not high. That can be approximated as by something like sigma is equivalent to y over r, and then r is nothing but Vc times Tf minus T, current time and the final time, and Vc is the closing velocity along the line of sight. So, arc is equal to Vc times Tf minus T obviously, and then Vc is nothing but Vm minus Vt or Vt minus Vm, depending on what people write actually. Okay, so if I mean it again depends on the what definition you have. If you typically if you have Vt minus Vm, there will be a sign change in the guidance law later actually. Okay, so Vc is the velocity component along LOS actually. So that is some typical geometry and then the concepts used in missile guidance. Now the whole idea here is I can nullify this difference between y. Okay, that has to go to 0. Whereas this direction it should also go to 0, then only it can happen, then only it can intercept. So, the y direction error will be killed through the formulation part of it, whereas x direction error will be killed through appropriate kind of estimation of time to go rather basically. Alright, let us move on to optimal missile guidance. How do you formulate that and all that? So, we a little bit comment that many classical missile guidance laws are inspired from observing nature, something like PN guidance and all that. Then there are control theoretic based guidance laws that are usually based on kinematics and or linearized dynamics, and that is what we are more interested in this lecture, to come up with optimal control theoretic guidance laws which are based on kinematics of the engagement actually. But they are usually not very effective, even though they can do the job with a larger warhead and all that, they are not very effective in general. So, the later subsequent lectures we will see how to make it more and more effective actually. So, in general optimal control theory happens to be a natural tool to obtain the effective missile guidance law, because we are equipped with a good formulation of boundary condition at the end. Initially something may happen, but at T equal to Tf we can impose boundary conditions that we need, and that's the platform it gives us for formulating a problem and getting a solution history of the control variable, in other words the lateral acceleration variable actually. So, typically people have talked about 2D point mass equations, we have talked about that in flight dynamics lecture also, that if you really simply take flat earth and non-rotating earth and that simply 2D point mass model, you can fix an axis system like that and come up with these two kinematic equations and these two dynamic equations. It does not, this part of the equation does not even talk about target dynamics, but what you really are interested is having some sort of a formulation where the relative dynamics is accounted for actually between target and vehicle. So, that let us see that very quickly, and then this is what we are talking is 2D optimal guidance laws using LQR. And here the engagement scenario again we will go back revisit and tell okay, what is my y double dot if I see that. Okay, y double dot happens to be something like 80 times cos gamma t. Okay, well 80 if you put a little bit. Okay, if you put a vertical axis, then again this angle is going to be gamma t basically. Okay. So, this is because 80 cos gamma t in the vertical direction minus am cos gamma n for the same reason actually if you put it here. Okay. Alright. So, we have talked about y double dot is like that. Again, you assume gamma t and gamma m, okay, is very close to 0. Okay. Then it so happens that cos gammas are 1 and you have y double t is at minus m. This is the dynamics in y direction that we will account for. There is nothing to do with any particular vehicle, and this is something called kinematic equation. In other words, I will confine myself to a generic formulation where I can generate this ATA accordingly, I mean AM accordingly basically. Anyway, so this is a small discrepancy also you can see here that VC, whereas y double dot is AT minus AM, the concept of VC that we are going to use in this lecture is VM minus VT, not VT minus VM actually. Anyway, so we can change it if you really like to, again the sign change will happen at the end actually. Anyway, so this is what it is. Now, let us quickly derive this true PN guidance using LQR. So, the system dynamics is, remember, this is y double dot, okay, is AT minus AM, and something like okay, let us not okay, let us have a small correction here. We will in our formulation purpose, we will also make it compatible rather. We will tell, okay, this is y double dot is AM minus AT concept actually. So, we will have plus AM minus AT. So, like that actually. That makes our life easier for derivation sort of thing. Okay, so this will go ahead, and then this y double dot is this restriction, this constraint, and first case that we will talk is AT is 0. The lateral acceleration command for the target that you are assuming is 0. That means target continues to move in the same direction basically. So, when you have target acceleration 0, then y double dot, which is v dot actually, y dot is v, so y double dot is v dot, so v dot is AM. So, this is the constraint actually. So, that what you are assuming is AT, okay, assumption is actually wrong here. Okay, what you are assuming here is AT equal to 0, okay, that is what you are assuming. Okay, so this is next case we will see that AT is constant and all that. Right now we will see AT is 0. So, this is why V dot is AM actually. Now, performance index, obviously I would like to have minimum lateral acceleration, I want to generate minimum induced drag basically. So, minimum lateral acceleration makes sense. So, this is what I want to minimize subject to these two system dynamic equation, very simple actually. Initial state is known to me, y naught v naught, and final state is also known to me. What I want to do is yf has to go to 0, whereas vf is free actually. Okay. So, if this is the very standard way we can start, and you can put some Hamiltonian and things like that. Essentially, you can see that it is also a LQR problem. Okay, this is a linear system dynamics with a quadratic cost function. So, you can directly get it using LQR theory also, and that is what we have done in one of the previous lectures. Using the state transition matrix solution and things like that. Now, here we will directly go through this Hamiltonian sort of necessary conditions and all that. So, we put Hamiltonian like this. Now, optimality conditions tells us that there are three things: state equation, optimal control and co-state. So, this is the state equation, and then optimal control tells us that del S by del AM has to be equal to 0. That means, lambda 2 has to be minus AM, AM has to be minus lambda 2 actually. So, once you get lambda 2, we are done, but how do you get that lambda 2? So, for that we have to see the co-state equation also. It fortunately turns out that lambda 1 dot is 0, because Hamiltonian does not contain y, whereas first state is y, and Hamiltonian is not a function of y. So, lambda dot is partial derivative Hamiltonian with respect to y, which is 0. So, lambda 1 is essentially a constant. Similarly, lambda 2 dot is del S by del V, which happens to be minus lambda 1, and lambda 1 is C1. So, we can put C1 there. The lambda 2 happens to be this one, minus C1 t plus C2 actually. Then here we can invoke this transversality conditions to evaluate this C1, C2 sort of thing. So, one of the transversality condition is lambda 2 at TF has to be equal to 0, because V of TF is free basically. So, now lambda 2 of TF is if you put T equal to TF, this is what it is. So, you get this constant equation, and hence C2 is nothing but C1 into TF. So, we have a constant equation, but they are not able to we are not yet found the values for C1, C2, then only we are done. We find C1, C2, then lambda 2 is known, and then lateral acceleration is known to us actually. So, how do we get that? One equation is available. What is the second equation? With that also you have to impose that y of Tf has to be 0 actually. For that, we need a solution of this conditions. Okay, so now we come back to the system dynamics equation, for where we want to integrate the v dot equation and then y dot equation, things like that actually. So, we have this lateral acceleration which is minus lambda 2 is something like this, minus C1 times Tf into T, the C2 is Tf actually, right. So, now put it C2 equal to Tf, it will turn out to C1 into Tf minus T. So, that is what it is. And then you apply, first find V and apply the boundary condition. So, V dot is Am. So, V nothing but this one, and Am is something like this. So, Am is substitute that, you get V dot, you got integrate one time, and then you will get something like Kv, which is constant of integration minus the integral of that, which is C1 times Tft, because of T is T square by 2 actually. So, now we apply the boundary condition that equal to T naught, V equal to V naught. Okay. So, that means Kv is nothing but V naught. So, Kv once you put that is, so that means V is nothing but Kv is V naught here. So, V naught minus this expression actually. Now, I go to y dot expression and then tell y dot is V. So, now V I know, V is something like this. So, I put it here and then we integrate one more time and tell okay, this is my y actually. And this integral constant of integration is evaluated again at the t equal to 0, and t equal to 0 you have y equal to y naught. So, that will give us that ky is nothing but y naught actually. And hence, it equal to t, I mean we got the value for ky now. So, the entire thing will turn out to be okay, but at t equal to tf, yf is also 0, that is the misdistance actually. So, there we want 0 misdistance in y direction. So, we put everything here, that is equal to 0. And this will give us the finally the constant that you are looking for is C1 actually. Okay, so C1 into Tf minus T, that's remember that is your lateral acceleration. So, now we got C1 here. So, then the optimal guidance law you can this is because it is like that, and I tell okay, I will define something like time to go, which is nothing but Tf minus T, which is repeatedly used in guidance literature. And also is the initial time is nothing but the current time, that so that means T equal to 0 I can assume. So, essentially time to go, sometimes it is written as capital T, sometimes as T go, essentially with the assumption that T equal to 0 is nothing but Tf actually. Okay. So, Am, okay, assuming that current time is the initial time, is nothing but something like this expression actually, minus 3 over time to go square times y naught plus v naught into time to go. Okay. Now, interestingly, it so happens that if you look at the engagement geometry and then you have this approximation sin sigma equal to sigma, the sigma is y over r, that is what we mentioned in one of the slides before. Now, if y over r is nothing but Vc closing velocity along r times Tf minus T. So, if you take sigma dot turns out to be like this denominator times dot of the numerator like standard formula. And it turns out to be like this. So, if you T1 T you cancel out and all. So, and Vc you take it this side. So, turns out that Vc times sigma dot is nothing but this expression. And this expression is something that we are getting here basically. Okay. So, that is why you are getting this kind of thing. Okay. Am equal to minus 3 Vc sigma dot. And also remember this is nothing but Am, and this small sign incompatibility, if you see that is a minus or plus, again depends on the definition of Vc. Okay, and here definition of Vc we have used something like Vm minus Vt, but if you take Vt minus Vm, then obviously it is going to be plus actually. Okay. So, this is what it is. So, Am, what you will end up with in this optimal control theoretic derivation is also the same Pn actually. Okay. So, this expression is the expression for this Tpn sort of thing. So, the beautiful thing about this guidance law is does not require estimation of the target acceleration. That means, and target acceleration is actually a very difficult thing to estimate really. Okay, target velocity, I mean position you can, velocity yes to some extent, but about estimating target acceleration is a different ballgame altogether actually. It will be too much corrupted with noise and the information may not be reliable actually. So, that the idea here is it does not even require that. So, whatever error in all is not able to, it will not respond to that actually. Okay. However, if you really know a large component of the target acceleration around which there is a deviation and all the small kind of errors and all, it is actually, it makes sense to implement that and then see actually. So, that leads to the concept of augmented PN, and where we are not we are telling that okay, AT is not really 0, but AT is somewhat constant. It is a bias term about which there are some errors and all which I mean I may ignore, but essentially I will not ignore the bias component actually. It means AT, the constant component, I am going to use it actually. Okay. So, if that is the case, then this is something like this assumes that AT is a constant, that means it will, and whenever some lateral oscillation is constant, it results in some sort of a circular motion behavior. So, that is what is called its circular motion target assumption and all that actually. So, anyway, so the difference here is instead of AM, it has become AM minus AT, everything else is same actually. So, the V dot has become AM minus AT. So, accordingly, there will be changes everywhere, and they will tell Hamiltonian is nothing but that is AM minus AT now, and nevertheless, the optimal control is still minus lambda 2. Now, that is not affected. Now, the same philosophy, we start with lambda 1 dot, lambda 2 dot, solve it, and lambda 2 will turn out to be like that. Again, transversal equation you put, same constant you will get. And then AM is nothing but that, but the value of C1 will be different here compared to what we had before, because the boundary condition is different actually. Alright. So, you follow the very similar steps, and when it really comes to the final boundary condition, it also remains same. The only difference is this V dot actually. V dot is this minus AT component is coming up, and that complicates the matter a little bit. So, now you can talk this V solution also contains this minus AT term, and hence every solution will also contain this minus AT term, AT times T. So, but the procedure essentially remains same. So, find the y. So, y dot is like this. So, you integrate and find y. Again, apply the similar boundary conditions, and you will end up with this kind of expression, where C1 turns out to be an expression containing fairly similar to what we had, one component, and then there is an additional component actually. Okay. So, then optimal guidance law accordingly will turn out to be like this. So, we go back and put everything there, and AM at T0 or T0 means current time actually turns out to be in this expression form. So, if you really simplify, try to simplify a little bit, you contain the first component, which is which happened something before. Okay, you can, for clarity, you can put it something like ATPN if you want to. Here, so that is, so augmented proportional navigation command guidance command is nothing but the same command which comes from true proportional navigation, plus there is a component which comes from the target acceleration 3y2 IT actually. Okay. So, this is good as long as the target estimation itself is good, at least the bias term is good actually. Okay. But if that is not good, then the performance can be inferior to PN also, remember that actually. Okay. So, when we talk about PN, I mean in this entire optimal control talk about TPN anyway. Okay. So, if it is, I mean if the target information is good, then this is supposed to perform better. If the information is bad, the performance can be worse actually. Very quickly, you can also see the ZDM sort of ideas, because that is what is used very rapidly, very vast amount in the missile guidance literature. The zero effort miss, this concept is something like the distance that the missile will miss the target if there is no corrective measure. Okay, so that is a very neat concept, and using that there are several ideas that pops up in even including current day literature actually. If you do not do any further correction, the direction correction of the velocity vector, let it go continuously wherever it wants to go, and then finally you will end up with some distance, and that is called zero effort miss, because there is no effort and whatever miss happened actually. Then obviously the missile guidance can be interpreted this way, the final zero effort miss at t equal to tf or t equal to 0, that has to be 0 actually. Okay. The correction should happen in such a way that the final ZDM should be 0. Anyway, so mathematically speaking, the ZDM can be interpreted something like this: YF minus this term, this is the predicted YF sort of thing, Y naught plus Y naught dot times T go, this is the predicted TF, predicted YF, and hence the z is nothing but yf minus this quantity. Okay. So, what is the ZM rate? That's what we want to impose as a system dynamic equation. So, z dot is this one, where you assume that yf is a fixed quantity. So, yf dot is 0, and then if you tell okay, this t go dot is nothing but minus 1. Okay. T go by definition is this. So, T go dot is nothing but minus 1 with Tf constant. Okay. So, that minus 1 if I put, this becomes plus y naught. So, these two terms also cancel out. So, it lands up with like something like this actually. Okay. So, y naught double dot times T go, and we also know that am is nothing but y dot. So, this z dot is minus am times T go actually. So, this becomes a constant equation to impose in the system dynamics as a system dynamics in the formulation. So, again this concept remains same. So, minimize the same lateral acceleration, but subject to this single z dot. Remember, this is a single equation now. It's not a vector. It's a scalar equation constant. So, algebra becomes much easier also in a way. So, we have this Hamiltonian optimality conditions again, co-state equation. It turns out that lambda is just a constant. And then optimal control, it turns out that am is nothing but T go times lambda, if you put it here, and then that's equal to 0. So, am nothing but T go times lambda. Now, the zero effort miss dot sense, this is the equation, z dot equal to that. So, am equal to that. So, you put it back here. So, z if you integrate it, it turns out to be something like this, and then you put the boundary condition that when T go equal to T go, initial T go, then z is z naught, and when T go equal to 0, finally, then z equal to 0. Remember, this z dot equation actually develops backward in some sense actually. Yeah. So, anyway, so this is if you interpret this, if you put these boundary conditions, then it turns out that kz is nothing but z naught. So, that this z is nothing but that, and then if you put additional boundary condition like this, then this is nothing but 0 equal to z naught times this one. So, lambda you can get a solution like this very easily. Once you get lambda, your am is nothing but T go times lambda. So, am is nothing but 3 times z naught by T go square. So, what we have interpreted that am in the previous lectures is something like this. Okay. It has been represented as something like this actually. It's either you can have am equal to this expression minus 3 by y over T square plus b by T, or you can have minus 3 V c times sigma dot, or the same expression we can write it as 3 times something like Zm by T go square actually. Okay. Alright. So, 3 equal to am is nothing but z naught over T go square. So, initial Z by T go square. So, if you somehow compute this z naught, okay, okay, so z naught, okay, z by definition is like that. So, z naught is if you put all these initial values of T go and things like that. So, if you compute z naught, that is every instant you compute the ZM, that is your current value of ZM, and then put it there, and you will get it what you want actually. Okay, not that. All right, let's go to that. Okay, so this is where we are actually. All right. Now, finally, well, we will also see different application and tell okay, can we really do something better, because we are using optimal control theory. So, going and finding out missed distance 0 is not the only condition actually. We need to do a little better than that. So, then this idea of terminal aspect angle constraint guidance comes. So, that means you are not only supposed to go to the target and hit it, but also you have to hit in a particular angle of the velocity vector. Okay. So, that concept leads to this terminal angle constraint guidance sort of thing. So, this is again different, we will go back to this formulation 1, okay, what we had with the target acceleration 0, but there is a boundary condition that is also changed actually. V of Tf is not free anymore, but V of Tf is just I mean this is the desired angle, okay, and using this V times 10 mu, if you put it that way, that is our V. That is what we want actually. V of Tf has to be Vf. And now, if you see this this entire formulation, I mean just a close note of it, we know this optimal control theory framework, and you know the problem objective. So, once you formulate this objective and put it in the proper mathematical framework, rest of the things are simply algebra actually. So, we do not have to break our head thinking so many things about geometric concept, how the trajectory shaping should happen, all sort of things. It will automatically take care of all those concerns through a mathematical formulation, and that is the beauty of optimal control, and that is why I call it is naturally geared up towards this path finding problem sort actually, and missile guidance should be naturally falls out from optimal control theory. So, everything remains same, only a little bit change in the boundary condition. Of course, when you account for this boundary condition, B of T f is that one, obviously your solution nature is going to change, you will end up with a different formula actually. Alright, so it starts similar way. Okay, again Hamiltonian is that, system state equation is like that, control is equation is like that. So, you have m equal to minus lambda 2. Then co-state equation, you have this lambda 1 dot is same 0. So, lambda 1 is C1, lambda 2 dot is again minus C1. So, you have the same expression for lambda 2 T also. Now, optimal control equation again similar, minus lambda 2 which is C1 T times C2. The question is how the C1 and C2 will be different here. So, we have this V dot, again we go ahead and solve the system dynamic equation now. V dot is AM which is like this, and hence V, if you integrate it, you will get something like this with the integration constant. But at t equal to 0, we know V is V naught. So, we have this kV equal to V naught. So, ultimately, if you put kV equal to V naught, then V is nothing but V naught plus C1 T square minus C1 T square by 2 minus C2 T. Question is we have to still know C1 C2 actually. So, we have this optimal guidance law, which is this for deriving that we need this expression for y also, because we want to utilize the boundary condition for y. So, we now put y dot is v, which is nothing but this, and then after integrating we will have this additional integration constant again from initial condition that t equal to 0, y equal to y naught, we will get ky equal to y naught. Okay. So, it will get from this expression we will get this expression for y. So, we have this expression for v and this expression for y. Now, this is this we now are ready for applying the terminal boundary condition, which is given in terms of Vf and Yf actually. So, at t equal to Tf, where y of Tf is 0 and v of Tf is Vf, that is what is given as constant equation for the problem. So, that means when you substitute this in this expression and that expression, we will end up with these two equations. Now, there are two equations and two unknowns C1 and C2. So, we can always solve for this, and after solving we will get something like this actually. I suggest that you solve it yourself. You can solve it either in a vector matrix formulation or simply using this method of elimination. There is only two variables anyway. So, you write C2 as a function of C1 and then put it back here and solve for C1 and then come back and solve for get the expression for C2. That is what led to something like this. So, we got everything that we wanted. So, that means this time to go information, again we put it something like this. By the way, this time to go, when somebody talks about, it is also like there are this critical parameter in optimal missile guidance, and normally you will take this is your LOS and something like r is my LOS distance. So, T go is approximated typically by r by this Vc. Vc is closing velocity, Vc is typically negative. So, normally we will put minus by r by Vc. So, this is the expression that is heavily used as approximate time to go, but there are many different ideas for estimating this time to go in a better sense. The argument is it is again getting updated. So, obviously, it will it is not that bad and it happens to be like that, but anytime you use you rely on this update sort of ideas, then the fluctuations will be large actually, and it will keep on getting different values at different point of time, and hence your entire magnitude will become different. So, your control oscillations will become more actually. So, to avoid that, it is better that you estimate a good T go which does not fluctuate much actually. Now, for that you have to assume circular path, this path, depending on the trajectory shaping that you are talking. Essentially, that talks about the entire path, the line integral of the path divided by average velocity on the path. Then you will get a very good estimation from T go. I will not digress too much on that, you are encouraged to read many things on that actually. But this is something that people conveniently use actually anyway. So, you define back which is T go and go back to the expression that our lateral acceleration is nothing but C1 T minus C2. So, we have got C1 and C2 now. So, we put it back here C1 and C2 and and simplify a little bit. That means, with T equal to 0, T go will turn out to be Tf and things like that. You simplify a little bit, it will turn out to be just T equal to 0. So, this C1 T will go and only C2 minus of that. So, it will turn out to be like this actually. Okay, so this is you can very clearly notice that there is a terminal miss component and there is a aspect angle component. This component came because of the formulation actually. So, you can see now the power of optimal control, and also in these 2D things it can be extended to 3D so simply by mathematical formulations and all that actually. So, that is possible also. So, that is what I mean, various things we can talk about while formulating the guidance problem in the framework of optimal control theory. So, some concluding remarks. In general, missile guidance turns out to be a very fascinating field in my view, and then the guidance concepts can be used for several applications, which is even more exciting. Okay, it is not necessarily only missile guidance. I have shown you various applications in one of the slides, including exactly the opposite problem, which is collision avoidance. So, that is also we can formulate and use it in a good way. Then linear quadratic optimal control theory offers a very good platform for optimal guidance, leading to very good closed form expressions actually. And obviously, TGO happens to be a concern, but various time to go estimation ideas exist in the literature which can be incorporated for better laws actually. Then extension to nonlinear formulations are topics of current research. Essentially, this beauty of closed form solutions will be compromised for numerical solutions, but as long as you get numerical solutions in real time, things should be alright actually. And those will be much more powerful compared to this linear approximation guidance laws, and there you will talk about the real vehicle dynamics as a constraint equation. So, then the solution nature will be much more relevant actually. So, we will see all that as we go along in this lecture series actually. So, with this application sort of one lecture, I thought it gives you a good motivation and ideas of why you want to read more. So, in the application sense, we can talk various challenging problems in general actually. Alright, I will stop here. Thank you.